Hello, AP Physics 1. This video is going to be about the Giancoli problems that you requested that you wanted to see additional solutions and walkthroughs for. Um, so here we go. You probably want to have a textbook, definitely, or online version available so you can also refer to them. So the first one we have is question 10. Let's pick a color of the day. So in 10, this is a level 2 problem. So we have a 380 kilogram piano, slides 2.9 meters down a 25-degree incline and is kept from accelerating by a man who is pushing back on it parallel to the incline. So first off, we have the mass of the piano being 380 kilograms. We have the distance that it's sliding for, whether you want to call that delta x, delta y, it's up to you. How you want to arrange that. So basic picture, kind of like what we have in the book. Here's our piano, here's our guy, and it's going down this 25-degree incline. And it's going down at a constant velocity because it's kept from accelerating. So it's moving. So work will be done because work is force times a distance, or when we apply a force over a distance to move it. So work will be done because the box and the guy are going to move. So part A starts off asking us to determine the force exerted by the man. So we're talking force diagram here. So we can look at it two ways. We can look at it as drawing a force diagram of the man or the force diagram on the piano. I'm going to pick to draw the force diagram of the forces on the piano. That way, my applied force going up the hill or the incline is going to be the force from the man. So we have the force due to gravity of the piano. We have the normal force from the ramp acting on the piano. And then we have, this is not friction, this is the applied force by the man. Cool, so those are all of our real forces. We need to determine components. So this is our force gravity in our newly defined y direction. Force of gravity in x direction. Again, these were the types of problems where we had to realign our axes. I'm just going to take those off just for ease of viewing. And this is bothering me. Cool. So it's important to note that the normal force is going to be equal to the y component of gravity, and the applied force from the man, I don't know what I'm doing too, is going to be equal to the x component of gravity, because again, we're not accelerating. So we can go ahead and start calculating. We know the mass of the piano, and this is part of the reason why we want to draw a force diagram for the piano, not the man, because we don't have any information about the man. So we know the force of the man on piano on man is going to be the same because of Newton's third law, but we only have information about the piano. So we have that mass, 380 kilograms. I'm going to use 10 for G. Oops. So it weighs 3,800 newtons. I know my angle in here is 25 degrees. So I could start solving for things. So to get the x component, the opposite side of my 25-degree angle, sine 25. Sine is opposite over over hypotenuse. So FGX over FG, which I already kind of defined, so I can make that 3,800 newtons. So my FG of X, if I plug that into a calculator, making sure I'm in radian mode, or sorry, not in radian mode, making sure I'm in degree mode, I get about 1,600 newtons, and that is also going to be the applied force from the man. Because of our force diagram, we said they were equal, so that's our answer right there for part A. For part B, we're looking for the work done on the piano by the man. And reading a little bit ahead, part C is looking for the work done on the piano by the force of gravity. So it's the same force because of Newton's third law, and they're moving that same 2.9 meters down that incline. So I'm just going to go ahead and solve for just the work. I'm not going to indicate whether it's for B or C, and you'll see why in a moment. So it's the force that we're applying. So whether we're talking applied force or I'm sorry, when we say force, we're saying either the applied force or the component of gravity in the x direction. So we know the magnitude of this value is going to be the same. So we already figured out that was 1609, and this is going to move 2.9 meters. Plugging that in, we get about 4, 6, 5, 7. We'll call it that, and that's going to be joules, because a newton times a meter is known as a joule, Joule. So now let's look in terms of man versus the component of gravity doing the work. So if you remember way back to those flipping physics videos when we looked at this equation here, they mentioned that if the force and displacement or distance, right, we can kind of look at it as far as this generally, if the force and displacement are in the same directions, that's going to be positive work, right? Because if they're both going in the same direction, why call them negative? However, if the displacement is the opposite direction than the force, that's going to be called negative work. So it's kind of like the man. So if we look at the scenario, and the man is sliding down the hill, right? He's probably not wanting to slide down this hill. So the force that he's applying, or let's look at it a different way, sorry, because we're not talking friction. So the piano is going down the hill, and so is the guy. But when we look at the forces, the force from the man on the piano is going up the hill. So in that case, the force on the piano by the man is in the opposite direction than the distance it's going. So kind of like maybe his job was to push the piano up the hill, because why would you push it? He's not doing his job. He's not doing his work. So the man, I guess I gotta do this, is gonna have negative work. So his work would be the negative 4,600 joules. Gravity, or the component of gravity in that x direction or parallel to the incline, that's going to have positive work because the force of gravity is going down the incline, and then also the piano is going down the incline. We could kind of look at, the work done from the piano on the man, but that's not part of this question. So the overall net work on the man is going to be 0. So this is going to be like, I didn't mean to do that. So if we combine these total, right? because these are the two amounts of work on the man. We get a network on piano as 0. Oh, that doesn't make sense, but hold on a second. We can also look at that in terms of forces, right? The net force on the piano is 0 because it's moving at a constant velocity. So if the net force on that object is 0, there can't be work done on it. Well, what is work really? So why would we, have this discussion? Why is this important? Work is also how we change or transfer energy. There was no energy transferred between our two objects, meaning the man and the piano. So that's why we would analyze this scenario. So even though the energies of them are changing, right? They have less and less gravitational potential energy, but just those two objects in the system acting on each other, they are not doing work on each other as a net, as an overall, because they're not transferring energy. So a weird kind of question. You'll see this sometimes as far as negative work, positive work, and it just has to do with, is the force that we're applying moving in the same direction? All right, the next one you guys had questions on was 18, I believe. Let me double check. Yeah, 18. So 18, some of these will go a little bit faster. 18 was a level 1 question, so you got to kind of think like, why are you asking the teacher to go over a level 1 question that's supposed to be kind of basic, like entry level, even like academic level for work? For this one, I think it might be just that conversion factor, maybe. Not really sure. So we're asked how much work must be done to stop a 925 kilogram car. So we have the mass, we have the velocity. It is in a unit that we don't like because we're going to be looking at work, which has newtons in it and it has meters in it. So we need to convert these to meters and seconds because there's meters and seconds hidden in a newton. So you can either kind of convert that on the side or simply Google it, since this is like a homework type thing. However you were taught to convert. Mainly, I like to use how I learned stoichiometry in chem. So it's 95 kilometers per hour. I'm going from kilometers to meters. So for every 1 kilometer, there's 1,000 meters. My kilometers cancel unit-wise. So I'm good there. Hours I need to cancel, and I'm going to seconds. 1 hour is 3,600 seconds. And I plug that all in, and I get about 26.4 meters per second. All right, so now we're good. We have this. So we're looking for work. And work, again, force times distance, or force times displacement. And it also equals the change in energy. So here we're looking at how much work needs to be done to stop a car, right? So it's moving, so we can calculate that initial kinetic energy and then subtract it from the final. Now the final is really easy. It comes to a stop. It's got no kinetic energy when it comes to a stop. So we can just simply look at that kinetic energy, be initial, because we can subtract the final, but we don't need to do that because we know it's 0. Probably should note that. Let me do that though. So we would say energy kinetic final minus energy kinetic initial, which we know our kinetic final is 0. Sorry, I need to write that. And what about this negative? That's important because it's going to be negative work, meaning the work done on the car is a result of a force that's acting in the opposite direction of motion of the car. Because your frictional forces are going in the opposite direction, so that's why that winds up being negative. So we're just simply calculating that, where we have the mass, 925 kilograms, our converted velocity that we have to square, and we get our work as negative, where we go here, 322,344 joules, which whenever we see some big numbers like this, it's sometimes worth noting that it's more correctly expressed in a different version of that unit. So we can do this as 322 kilojoules. We just divided by 1,000. In case you ever see that kilojoules used in a problem. So that was 18. The next one we have going is 23. 23 is a level 2 problem. Kind of similar to the last one. So we have at an accident scene on a level road, investigators measure a car's skid marks to be 78 meters long. So the distance of the skid marks is 78 meters long. It was a rainy day and the coefficient of friction is estimated to be 0.3. This is going to be kinetic friction because we're sliding. Oops. And that's all the information we're given. We have to use this data to determine the speed of the car when the driver slammed on and locked the brakes. Why does the car's mass not matter? They could be kind of hint there. So this is also why you don't want to lie if you get into a car accident, because they can go back and do the physics and prove that you were speeding or that you didn't stop at a stop sign or a red light. So let's think of the scenario. We're moving, so we have kinetic energy in the beginning, and then the car comes to a stop. Well, what makes the car stop? Work. So in the beginning, whatever kinetic energy we had, that was all converted to work. So kinetic energy, 1/2 mv squared. Work is force times distance, or displacement if you want to put that. I don't know, for some reason, I feel inclined to put distance for some reason. I'll have to take a look at what's on the AP sheet. I think it actually says distance. I don't want to just leave that by itself as far as force, because it's a frictional force that does the work. So let's go a little bit further, because I don't have the force, right? Well, draw a force diagram for the car. And let's say the car is moving to the right, so friction would be going to the left. Cool, there we go. Normal and gravity are equal. Well, remember, force of friction is mu normal force. So we can add that into our derivation, where mu normal times the distance that we skid. Well, normal force is equal to gravity, or force due to gravity. So this is where that mass disappears. So Fg equals mg, right? And this becomes a mass party equation where the masses don't matter. And I don't know why I wrote a G. I'm like writing things I'm talking. Sorry. And we have all of those values, so we can go ahead and plug them all in and solve for our velocity. I'm going to use 10 for gravity, acceleration due to gravity, that is. Plug it all in, take the square root, and we get a velocity of about 21.6 meters per second. And if that was above the speed limit, guess who's at fault for the accident? Let's see. Next one we have is 29. Level 2 problem. We have, we got a hiker, so we're going to need to draw a mountain. Okay. So we have a 66.5 kilogram hiker. Starts at an elevation. So if this is our 0 mark elevation, and he starts at around 1,270 meters, and he hikes to the very top, which is 2,660. What is the hiker's change in potential energy? So we're not really concerned with anything below here. We're just looking at this portion of his trip. So that's why it says change in potential energy. So what's changing? His height is. So you can either do it as like gravitational initial or final minus initial, or just subtract those two heights because the mass of the climber and acceleration due to gravity is going to be the same. So I could do something like this. Just to save some time in writing. This will be change in gravitational. Use 10 for G. And I would do 2,600. Gonna run out of room. Minus the initial height he started at. Plug that all in, and I get my 924,350 joules, which I could also express that as 924 kilojoules if I wanted to. So then we have part B. What is the minimum work required of the hiker? Well, we know work is equal to change in energy. So if we have that change in energy, gravitational, that's going to be the same as the amount of work that he's going to need to do to climb the mountain. So easy for B. For C, can the actual work done be greater than this? Explain. So the answer is yes. And just looking at physics-wise, he might be, stepping up and down over rocks or boulders or fallen trees, and that's going to be energy he's not getting back. So even though he's going from this point A, B to, this one elevation to the other, he might be going up and down over that course of that trip. He could go like, up like a steeper incline, not that, and then go down and then come back up. Who knows? There's also friction involved between his feet, his joints. There's also biomechanic stuff and biological processes happening that require work. So we can also look into that as well. So it will likely be more than that. So a lot of times when you're just looking at basic physics problems, it's just like this thing is going from point A to point B. We forget that it's living, has other things going on. There's friction. And we were looking at a snapshot in the beginning and then in the end as well. Next problem we got, let's see, is 33. Almost done. 33, now level 2. So we had a sled is initially given a shove up a frictionless 23-degree incline. It reaches a maximum vertical height 1.22 meters higher than when it started at the bottom. What is the initial speed? So here's our incline. It's 1.22 meters high. We're looking for what the velocity is, or no, sorry. We know when it gets to the top, right? It's going to go all the way to the top and come to a stop eventually because its kinetic energy runs out. We know this is 23 degrees. So if this is our sled, I don't know what kind of sled it is. It's moving. It has some velocity that we're looking to find. And it was already released by the person. So the person was like down here and pushed the sled up. So the moment it comes out of their hands, or thinking of the projectile motion lab way back when, the moment that that ball left the launcher is what we're looking to find the velocity of. So energy-wise, in the beginning, right when it leaves the person's hands, it's got all kinetic energy, and then that gets converted into all gravitational when it gets up at the top position. So it's just like throwing a ball straight up. We've looked at those scenarios before. So we know the equation for kinetic, we know gravitational turns into a mass party. Take mass from everybody. We're looking for that initial velocity in the beginning. We know g, we know that height. Do some basic math. Oh, didn't mean to put the square there. And we get about 5 meters per second. Next on our list, 47. There's 47, turn my page up. Yet another level 1. I'm a little concerned with seeing level 1s. That after you look at the solutions that are already there for you, I know sometimes they get a little bit more complicated than they need to be. But these are ones that definitely assign it, like, if you're requesting level 1 problems to see why you are asking them. So here we have a 16 kilogram child, slides down a slide. It descends a slide, 2.2 meters high, starting from rest, and reaches the bottom with a speed of 1.25 meters per second. So there's no picture, and I definitely think drawing pictures can help. They don't have to be, as you can see, very detailed. So the child starts up here, and this height is 2.2 meters high. Initial velocity is 0. Down here, he or she is moving at 1.25 meters per second. So looking at the energy, or let's see, something else is happening here. How much thermal energy due to friction was generated in this process? So think back when we did our pie charts or our bar graphs. That's what all of this is. So in the beginning, at the top of the slide, the kid has all gravitational energy. In the bottom, that's where they're going to be going the fastest. It's going to be all kinetic if there was no friction, but in this case there is friction, so we're going to have that thermal energy. So then going through and just plugging in our equations for them. Now there is no equation for thermal energy physics-wise, so that's what we're just looking for, is just what is the thermal energy that was generated. So this is not a mass party equation. I'll just move everything over. tend to gravitate towards the right side. So plugging that in, solving, we get around 339.5 joules. Now comparing some of these, like I did the math a little bit differently. 352 joules of potential, gravitational potential, only 12.5 of kinetic, and 339.5 of thermal. That's a lot of thermal for this scenario. Well, think of it. For most slides, they don't want you really going fast at the bottom. Like that's kind of disastrous for kids. So really for slides at the bottom, they kind of level out before they totally drop off, right? So that's why at the end there's going to be enough kinetic energy for the kid to make it off the slide, but not enough kinetic for them to totally fly off. So that's why, friction is involved. And if you've ever gone down a slide with a pair of shorts and you had your legs down and you got like the back of your thighs or your calves kind of on a slide when it was like either kind of sticky or really dry or hot, then you've experienced that friction, that thermal energy. I may have, had some of you guys have flashbacks from a little kid from traumatic experiences with that, coming to an abrupt stop on a metal slide. 2 more to go here. So we're going 57. Right here. Yet another level 1. How long will it take a 2,750 watt motor? So we have our power to lift a piano where we have the mass to a 6-story window 6 meters above. 16 meters above, sorry. So power is work per time or change in energy per time. So this one, kind of looking, we have masses, so we might be able to get forces. So let's look at it this way. Force times distance over time. And yeah, we can calculate that. We can take the work done divided by the, oh wait, does it tell us the time? No, we're looking for the time, sorry. So we have our 2750 watts. Keeping in mind a watt is a joule per second. So our force here is going to be our force due to gravity. So it's going to be mg times the distance that it was moved. It was moved a vertical height, so we can put delta y. Or feel free to put a d for distance there. All over time. So we have all that. So we have the mass. Where'd it go though? 385. 16 meters, I think it was. Yeah. And we're solving for the time. And we get about 22.4 seconds. So does that make sense? We have a motor lifting a piano up some height to go into a house or something, or an apartment building. 22 seconds, yeah, that's probably reasonable. 16 meters is not all that high. Yeah, so that's believable. And the last one that we're going to do that you guys requested was 69, which is another level 2 problem. This one definitely gets asked a lot over the years, just because of not necessarily the difficulty, but the complexity of what's happening here. So we have a skier getting pulled up the slope, or actually, as you start to read, there's 30 skiers. So a bunch of people going up this slope of, they're gonna go up here, 320 meters, and the skier is 65 kilograms, but there's 30 of them, so we're gonna have to multiply that by 30 at some point. We have the angle of the slope, and we have the mu. So they're being pulled. They're basically holding onto a rope. There's a motor, and they pull them up. So if you ever go onto a ski hill, if it's a somewhat gentle slope, you don't get on the actual ski lift. It's just a rope that you actually hold onto, and it pulls you up that gentle incline. It's usually not that far of a distance. And multiple people are holding on like so many feet apart. So that's where the 30 meters comes in, or the 30 skiers comes in. Mu that day, 0.10 between the skis and the snow. The time it takes to go up is 2 minutes, but we need that in seconds. What else do we know? We're looking for the horsepower. Well, we've never really discussed horsepower. Horsepower is, like a British unit. Like it's used a lot in vehicles and cars and engines, motors. So we're just going to calculate it in watts and then have to look up some conversion factor for horsepower. So it's a power problem where it's work over time or change in energy over time. Now, some people say, well, Mr. Ford, can't we just like figure out this vertical height and say it's going from no gravitational energy to a bunch of gravitational energy and just do it that way? Only if we weren't including friction. Because there is a frictional force that we're doing work against, unfortunately. So we can't do it that way. So we have to actually go up like this direction, this path. Let's see, we have the math, we have that. 30 skiers is important to note. So we're not going to go the energy route, we're going to go the work route. So work is force times distance over time. So we need to find out yeah. I wrote the wrong thing. We got to determine what forces we have here. So what forces are doing the work on the skiers? Well, there's the tension in the rope, right? That's pulling them up. But what other forces are involved? Well, let's draw a force diagram for the skier or skiers. So you got force due to gravity acting on the skier. You got the tension force or some other kind of force. I don't know if you're going to call it like applied. Depends on how the ski lift is designed. I'm going to call it tension because we're just going to hold onto a rope. We have the normal force from the slope. And then we also have some friction. So it's going to be the motor is going to be at the top of the slope, right? So there's going to be a force going up, tension. Well, there's no equation for tension force. It's going to be equal to some other forces. And we were given mu, so maybe we got to look at force of friction. And we're also missing out that we have to determine component forces as well. So normal and gravity are going to be equal, gravity in the y direction. And then the sum of the tension force, so that tension force going up the hill, is going to be equal to the sum of both force of friction and gravity in the x component. So that helps us set up our equation. That the power is going to be the force of friction plus the force of gravity in our x direction times some distance over time. So we're given some information to be able to do that. We're given an angle, 23 degrees. So however you would, determine this force of friction and gravity component, whether you do it like up in the problem, if you do it as like a derivation, that's kind of up to you because we do have the mass. Sometimes you can just find out the work done for one skier and then multiply that by 30. I just kind of said, well, I imagine we just have all of our 30 skiers like in one place and did it that way. So I went 30 times my mass of, what was it? 65 kilograms times G. And I got my force due to gravity being about 19,500 newtons. So that's the weight that we're pulling up this hill. But we need to know a component of that. So this is how I kind of went through and did it. Power is force of friction. No, I did it the opposite way. It doesn't matter. So don't forget force of friction is mu normal. And I'm kind of disorganized in this. I don't know why. I'm not all putting it in the same spot, maybe just as far as the thought process. And force of friction, in this case, is mu FGY as well, because those two forces were equal. So my force of friction would be mu, which was 0.10, cosine, because I'm looking at that adjacent side, 23 degrees, like this adjacent side here, right? My huge weight that I have here, 19,500 newtons. And I'm going to add that to my force of gravity in the x direction, which is going to be sine 23 degrees, times my weight, or my hypotenuse, if you will. All of that multiplied by the distance, which was the 320 meters, divided by the time. Was this the 120? So yeah, 120 seconds or 2 minutes. And then we can plug all that in, get a power of 25,105 watts. But for us, we're not really, familiar with watts. Maybe with light bulbs, but maybe not with like engines and things. So maybe we need to convert that. So if we look up a conversion factor from horsepower to watts, 1 horsepower is 746 watts. If it was like a test or a real IAP exam, they have to tell you that in the problem. But I don't think they would ask you to convert. So converting that, I'm just going to come up here, save some space, some time. So my 746 watts per 1 horsepower. Plug all that in, 33.7 horsepower, which kind of a powerful motor. Most lawn mowers are like a 5 or 10 horsepower motor, if it's like a push one. So to pull all those people up that incline, that makes a little sense. Cars, vary, but like a race car might be like a a 400 or 500 or more horsepower car. Cool. So if you have questions, feel free to stop in during office hours at some point, or ask me a quick question during class. Have a good night.